This video is presented by Industrial Testing and Laboratory Services. ITLS is a Pittsburgh-based, multifaceted business providing commercial-grade dedication materials testing services and non-destructive examination and quality control inspection personnel to the nuclear industries.
Hi, I'm Marty Wenzik, and this video is an introduction to our alloy identity training class. Alloy identity testing is a little more than just positive metal identification. It'll address other principles used such as thermoelectrics and electromagnetics. But most people think of alloy ident testing as the same thing as positive metal identification or PMI. And I'd like to make an example, show you an example here of why it's a little more than just that. So I have 1, 2, 3 pieces of material, and what I'm going to do is I'm going to start off with an X-ray fluorescence spectrometer or PMI gun. It's going to take a reading, a chemistry reading on material. So here's what I'm going to do. I'm going to use this since you can't see the whole thing. I'm going to do the big one first. Okay, so I set my gun down on it, fire it, and hold it there and wait. And the longer you wait, the better the numbers get, but within a short period of time, in this case, it shows me that this material is 17.4. So as you see there, so 17.4, and by the way, 17.4, the numbers 17.4 are the predominant elements in the alloy, the stainless steel here, which is 17% chrome, 4% nickel approximately. So, and it's also called 630, AISI type 630 stainless steel. So these two pieces of material, although smaller, are also 17.4. Okay, just so you know that. So a 17.4 stainless steel, what I'm using here as an example, is a martensitic stainless steel. And it is a heat treatable stainless steel. It's also magnetic. You can heat treat it to change its mechanical properties, to change its strength, to increase it. Reason you do that would be in the fact that 17.4 can be used to support design loads that are the equipment is being used in either corrosive environments or elevated temperatures, maybe up to 600 degrees. And the industries where 17.4 is used primarily is in the chemical, the petrochemical, the nuclear, and the aircraft industries. So for what we've seen so far, using the PMI gun or the X-ray fluorescence spectrometer, we can measure chemistry on these parts. And we know they're 17.4. But what we don't know at this point is the material condition. Are they solution annealed? Is the material solution annealed, or is it precipitated hardened or age hardened? And if so, at what level? That makes a big difference, because if you intermix your material, what could happen is you could inadvertently use solution annealed material, which is softer and has less mechanical properties, not as high as the hardened condition, and that means you could make components out of 17.4 that could subsequently fail. So in order to determine material condition, we have to do a little bit more than just taking a PMI gun or an XRF spectrometer and measure chemistry.
In this video, we're going to be discussing 3 different material conditions of 17.4 stainless steels. We're going to talk about the solution annealed, SA, age hardened, AH, or annealed with an hardening less than 900 degrees Fahrenheit, called APH. Now, the ways of being able to discern these material conditions, if you would ever have your material mixed up, is using a thermoelectric principle or an electromagnetic principle. So the first one I'm going to show you is thermoelectrics. We have an acromag metal tester here, and on the copper block I have 2 pieces of material. This is solution annealed, this is age hardened. Now, it's an analog screen, and when we read with a copper probe attached to it. So when we read it, what it's doing is it's generating a finite amount of heat, known heat, and we're measuring resistivity on that with known heat, thermoelectrics. So in touching the first part, I'll move this over so you can see. I touch, and the solution annealed gives me a number in the 30s, about 34 measurement on the analog scale. So when I touch the age-hardened piece, I get a number 55, 56, 57, we'll say. Significantly different. There's no way to tell to mix those two up. It's very easy to tell the difference between age-hardened and solution annealed. So I'm going to remove the age-hardened, and I'm going to replace it with an material APH. Again, just to show you on what the differences are here. So on solution annealed, I hit, again, 30, we'll call it 34. Okay, so when I do on the the APH condition, I'm sorry, on the APH condition, I measured that 33, 34. You see, so what this shows you is unto its own, thermoelectrics cannot differentiate between solution annealed and condition APH. Okay, we certainly can find the age-hardened material, but if it's solution annealed or the APH condition, we have to go somewhere else. So I'm moving things around here so you can see so you can see all this, and we will use eddy current or electromagnetic testing. And I'm moving this around so you can see the standards, put them in place here. Okay, get the logo in place because you've got to know who the company's talking, that we're talking here. And so we got this. Okay, there you go. So in the machine here, on the eddy current machine, I have it set up so that, I'll erase everything, so that my starting point is on the far right of the screen and rather low. You see a little dot there. Okay, just barely discerns. So when I touch a solution annealed, I'm going to start off with in the middle, my solution annealed standard, I get a response back where you can see the wave went from the starting point and went down low. It went below that, which was about 20% screen height, went down to almost zero. Okay, and if I clear it out, I'll show you again. Okay, repeatable. Now, third time, but I'm going to add something now. Third time, same thing. Now I'm going to leave it on there, and I'm going to touch the age-hardened piece, which is on the left. Pretty close, pretty hard. You see the difference now on screen height went from 0 to maybe 10. That's kind of close, okay? Again, just for demonstration, solution annealed, age-hardened. Okay, so now our problem was differentiating solution annealed and APH. So solution annealed, and now I'm going to touch APH. See, APH goes up there close to 50% screen height, between 45-50% screen height. So it definitely has a different waveform on here. Again, and I'll do it backwards. APH, solution annealed. So it's the combination of thermoelectrics, which does one separation, and then eddy current or electromagnetic testing does the second separation to be able to clearly separate solution annealed, age-hardened, that's age-hardened any heat treatment above 900 degrees F, or APH, which has a heat treatment less than 900 degrees F.